Freiburg, Frank Kutter's lab, defines AutoML as providing methods and processes to make machine learning available from non-experts and to improve efficiency and to accelerate research on machine learning. And here, the pointer works now. The emphasis is really on availability, so the democratization of machine learning, so allowing non-experts to tap into the technology as well as improving efficiency. On the other hand, if you look at Wikipedia, it states that automated machine learning is the process of automating end-to-end the process of applying machine learning to solve real-world problems. And so here the emphasis is very much on end-to-end automation and solving real problems. And as you can already see, there's not a whole lot of overlap between these two definitions, right? And there's no big surprise that there's actually quite a bit of confusion in the community of what AutoML is able to deliver and what it actually entails in terms of problems. And so me and colleagues, we often get questions asked from peers that look like this, right? So will all data scientists lose their jobs soon? And without taking too much away from the rest of this talk, the answer to that is going to be no. However, I do think and I do claim that automated machine learning can substantially change how data scientists and how we work in the future. AutoML is all about neural networks generating neural networks, right? So one of the main takeaways also I want to have from this talk is that pipeline optimization, like we've seen in the great talk on Monday from Noy and what I will show you later on here as well, is a significant part of automated machine learning, but it's only one piece of this AutoML puzzle. And last but not least, data science machine learning requires serious human expertise. How can AutoML ever be better? Well, that very much depends on what our definition of better is, right? Is that performance on a single data set, or is that, for example, performance consistently across a variety set of problems? Good. So given the audience and that we are on our algorithms track, I'm going to fast forward over that slide and I'm going to jump right where the magic happens. So if you look at this data science, the analytics process, all the way from the left, from where we take our business problem and we frame it into something that's amenable for machine learning, all the way to gathering, acquiring the data that we need, to building the models, to then deploying these models and then consuming the predictions as well as monitoring these models. So when we look at this process, when we talk about automated machine learning, we really talk about optimizing end-to-end this whole process, right? And currently, from a data scientist perspective, not all these steps here are actually equally enjoyable. There are surveys that indicate that the bulk of the time of data scientists is actually not spent in building machine learning models. It's actually spent wrangling data, doing data acquisition, data preparation, sometimes even annotation. And other surveys show an even more alarming picture, which is basically that as much as 85%, I think there's actually even more, of the data science projects never make it to production. So they never really get through this whole process, right? And if you ask me what's the biggest barrier right now for the proliferation of machine learning, then that's right there. Good. So automated machine learning to the rescue, right? Unfortunately, not quite. Current research in automated machine learning is very much narrowly focused on this middle stage here. So feature engineering, modeling, model tuning, model selection, right? However, as I mentioned before, we really need to be focused on kind of end-to-end optimizing this whole process, right? And so what I want to do in the remainder of this talk is to basically go through key challenges along the way, right? And if possible, kind of highlight state-of-the-art solutions, but in many areas, actually, there are no really solutions out there. It's still very ad hoc. Good. So let's maybe start on the left-hand side with problem framing. So problem framing is, again, it's like what we want to do here is take this business problem and break it down into a form that's more amenable for machine learning. And obviously, this requires a whole lot of human input. However, automated machine learning systems, they can provide a lot of guidance and guardrails along the way, right? So primarily to avoid quote-unquote operator error, right? So examples here include things like analyzing the response. Maybe, based on distributional characteristics, you might want to recommend that a user should pick a specific loss function, right? So if you have a regression problem and that is highly skewed, right? You might want to recommend to a user that they want to optimize for relative error rather than absolute error, right? Or your regression response is min-inflated, right? again, might want to choose specific loss functions for that. So there's actually, there's a lot of expertise that goes into this one step here, right? And helping the user kind of navigate this space is hugely important in automated machine learning. The next problem is data preparation. So again, current machine learning technology usually requires data to be in some kind of denormalized form, right? So usually a table or a data frame of data, but data usually doesn't live in that form, right? Usually it lives scattered across a variety of data sources, right? And the process of kind of wrangling all this data together and get into a form where we can use it for machine learning, that's called data preparations or data prep for short. And it's something that's often done manually. It's often even done outsourced to data engineers that use common ETL tools to solve this problem. But that can actually provide huge problems because these tools have not been designed for machine learning, right? And one of the problems one often sees there is that when doing data preparation, you might make mistakes that you peek into the future, right? So the classic example here, I once competed in the Kaggle competition where the goal was to predict the arrival time of flights. And we had a data set, historical flights, continental US, for a couple of months, right? So in order to predict the flight time, for each individual flight, you had to pick a point at its trajectory, and from that point on, you want to predict when the flight's going to arrive. But obviously, when you do feature engineering here and gathering, we could use features from ASDI, tracking information from weather stations all over the continental US, etc. Obviously, you only are allowed to use information that's available at this cutoff point that you choose. If you choose information from the future, for example, what's going to be the ceiling of the clouds at the destination airport at the time when you actually land, then you committed to something that's called leakage. So you peeked into the future, and it's really hard to recover from that. Just recently, actually, there is more and more work in this area that directly tries to tackle that using automation. And one seminal study here is from a group of MIT. It's called Deep Feature Synthesis, and there's actually an open source project called Feature Tools that goes with it. They also spin off a company shortly after. And the main idea here is that you give the system as input a star schema, a relational schema, and the system, it's relatively ad hoc, but it uses kind of a recursive approach to kind of create a very large set of potential features by applying aggregation functions from a library, and then you put that into your machine learning model, and you do obviously feature reduction to reduce the amount of potential features that you get. So this is a hugely important area in automated machine learning and very much underrepresented in research right now. The next step, partitioning. So again, one of the experience I had from running in these data mining competitions is that data mining competitions are often won using very creative feature engineering, but they're usually lost by making mistakes in model selection assessment, right? And so model selection assessment is commonly done these days using holdout data, right? But deciding which data you want to hold out is actually highly non-trivial, and it's very problem dependent. So any automated machine learning system that is of practical use, it needs to support, it needs to be very flexible when it comes to this, partitioning and designing your holdouts and your validation data sets, right? So classical examples include things like, your rows might have groupings, right? So a classic example in medical imaging, you have lots and lots of medical images, but only taken from very few patients, right? So if you want to really generalize to new patients you've never seen before, you better make sure that no patients leak in, from the holdout set into your training set. And similar things when you do when you work with temporal data, right? So when you have seasonal components in your data, you might want to make sure that your holdout or validation data at least has one seasonal component. So there's a lot of guardrails and guidance again that automated machine learning systems, I would argue, need to provide to be useful here. But again, it's very hard to do these things fully automated without some level of human input. feature engineering. So this is actually one of the areas that data scientists often claim to be more enjoyable parts of doing data science. However, that's also one of the areas I would argue that using automated machine learning technology and better modeling approaches like neural networks and gradient boosting largely, gets kind of automated away, so to speak, right? And again, here leakage is basically your enemy, right? So using frameworks for devising, quote-unquote machine learning pipelines to avoid leaking into holdout data, validation data is really, really key. And so if you look at modern machine learning models, they often look like this, right? Fairly complex graphs of different feature extractors that basically, pull signals out of your data and eventually put it into a two-dimensional array of floating point numbers, and you then feed that information into your neural network or into your gradient boosting model. And this is commonly referred to as a machine learning quote-unquote pipeline, even though it's not really a pipeline. And modern or state-of-the-art research in automated machine learning very much focuses on how we can navigate and how we can actually navigate this graph landscape, right? Search over a vast number of these graphs very efficiently to find the best possible graph for our problem. Now, picking which model you actually put then, also into the graph, that's, also a problem that sometimes is handled in isolation, but it absolutely should not, right? There's a huge dependency between what feature engineering you do and what modeling approach you choose. So it's actually not two different problems, but it's really one problem. One of the things that is also seen that you see in many AutoML systems is that if you want to optimize for accuracy, if you search for models and you build a lot of models, what you actually want to also take advantage of is that you can then take all these models, put them together in something that's called ensembling to create very accurate models, but those are also usually fairly complex and very hard to deploy, right? But they still give you the benefit of sometimes getting an upper bound on what's possible in performance, plus there might be, or there is more and more research also in being able to take very complex models and compress them down and basically improving their quote-unquote deployability. Model tuning, that's very much the homestead of automated machine learning today. It kind of started out very much with hyperparameter tuning. So, think of our models as basically just black boxes with a couple of knobs on the outside that help us to, kind of tune our models to get best performance. And hyperparameter tuning basically just refers to how we set those knobs properly. And as I mentioned before, really the state of the art right now in machine learning is to not only specifically optimize these single nodes or this one, our gradient boosting model or a support vector machine, but rather optimize the complete pipeline. In the case of neural networks, that's often also referred to as neural architecture search, right, where you basically learn the architecture of the network. And there are different approaches to do that. I want to walk through some of them so you get a better sense on how they work, and then basically present to you a bit what's currently state of the art in terms of solutions here. So I'm curious, who of you has actually used Bayesian optimization already? Okay, so only very few. That's great, because that's one of the staples from hyperparameter tuning and automated machine learning. So it's definitely a great tool for your toolbox. Bayesian optimization is an optimization technique that basically can be used for global optimization of very expensive objective functions, right? So the way you can think about this, actually, if you want to prospect for oil or for gold, right? Prospecting and drilling down is actually fairly costly, right? So you want to carefully trade off how often you actually have to drill. And so in Bayesian optimization, what we do is we take a Bayesian approach to this, and what it means to be Bayesian is basically to update our beliefs, right? So it's a loopy, so it's an iterative process. We're going to start with a random set of observation or evaluations of our objective function. So I tried to show this here on the right-hand side, but I'm not sure if the graph comes through nicely. But here, the red curve, so the red dashed line, think about this, that's the objective function we want to optimize over, right? Obviously, we see it now completely. And we have now randomly 1, 2, 3, 4 red points where we actually drilled down, right? So we evaluated that. And so given these observations, what we're going to do is we're going to build a surrogate model, right? So that's, again, a machine learning model, by the way, right? And then we use that model to, and it approximates the objective function that we don't know, right? And then in the next step, what we do is we're going to interrogate that surrogate function, that surrogate model. That is cheap because that's just running predictions, right? And so in our case, the surrogate model is the green one, and it has a nice property. It's actually also a quote-unquote Bayesian model, so it gives us the full posterior of the prediction, right? It not only gives us where the model thinks that the objective value actually is, but it gives us the prediction interval, the full interval, right? So you see that by the green curve here. So where the green curve is very wide, it means that the model is very uncertain, right? And where the green curve is very narrow, it's very certain, right? And so obviously what we want to choose now is where is the best place to next drill down, to next pick our point, right? And we want to do that by basically trading off exploration versus exploitation, right? So first, probably we want to do more explore. We want to figure out, okay, where are different areas where we don't know yet what the value might be. But as soon as we found some good values, we might want to, continue exploiting that area, right? And so that's a common method that's used for hyperparameter tuning. You can use that to optimize complete machine learning pipelines by basically building an Uber pipeline that contains all other pipelines. And then you introduce hyperparameters that are conditional, right? So they turn off specific sub-graphs. So that's obviously a big problem because your hyperparameter space is going to become massive, right? And so the way Bayesian optimization is often used in automated machine learning these days is to very much, when you already narrow it down on a couple of candidate pipelines. But this is the approach when you want to get very good final performance. Another approach that you could use is genetic programming, right? So genetic programming is a technique that allows you to, quote unquote, automatically program, so build functions using evolutionary algorithms, right? And so the main idea here is that we basically start with a generation of machine learning pipelines, and then we have rules how we can mutate these pipelines, or we can also cross over from one generation to the next, right? And then we run a couple of generations. And this system should allow, basically allow us to completely dynamically build pipelines, right? So there's actually a really interesting piece of work by Randy Olson. He's the author of Teapot, and also there are a couple of publications that go along. So if you're interested in this area, definitely check this out. It's probably not amongst the most effective techniques right now because it requires a lot of iterations. The next step, MultiArmed Bandits. Next idea is MultiArmed Bandits. Here, the basic idea is as follows. You represent each pipeline as an arm in a multi-armed bandit problem. And the goal in the multi-armed bandit problem is basically find the arm that gives you the highest return for your kind of investment budgets, coins you put into the armed bandit. And so in this case, we also want to basically, we get a budget, but in our case, there's no notion of just putting a coin into an arm, right? So this was initially proposed in the context of neural networks, where neural networks, you have a way to iteratively train them, right? By just running an epoch, right? And so the idea here would be that you start with 10 different neural networks. You spend a couple of epochs in each of the pipelines. You see how well this model is doing, and the higher, the ones that are not performing so well, you're going to throw away, and you keep on using the ones that do best, right? And so now the question is how you can do that with models that don't have this iterative training approach. Well, one thing you can do is you can do sampling of your training data, right? So that's something that's commonly used here, and actually state-of-the-art solutions use this approach very much right now. Another one that we've seen on Monday, actually, in Noise Talk, is Metalearning. Here, you actually try to predict how well a pipeline might be doing on a given problem. So you literally build a model that tries to predict, given a pipeline and a problem, how well it's going to do. And then what you often then also use is portfolio optimization to figure out, which are the pipelines might be complementary, and you use that as a seed set for many of the other methods we've seen before. And it basically comes down to state-of-the-art solution these days in automated machine learning are very much hybrid systems, right? So they use many of these ideas that I've shown before, maybe meta-learning to initialize the search space, right? And then successive halving, so these multi-armed bandits to winnow out these pipelines very quickly, and then use Bayesian optimization to kind of do the, get very good final performance. And then lastly, you build ensembles on top of all of them to get like an upper bound on model performance. So that's currently kind of state of the art. If you're interested here, check out this presentation, this paper. That's currently state of the art approach on some academic benchmarks in this area. Good. So that was model building. I'm gonna fast forward a bit. Some other aspects that are still very important here. I just want to talk about this one real briefly. Model maintenance is probably one of the frontiers currently for automated machine learning. As we know it, on the one hand, our machine learning models are just like software components, so they have contracts to upstream components that produce data, right? And sometimes these assumptions, they might not hold anymore. For those of you who've seen the talk in the morning by Yoshua Bengio, he mentioned, this regime when suddenly the test distribution doesn't match the training distribution anymore, right? We somehow need to be able to automatically detect when this drift happens, right? And basically counter that, if possible, fully automated, right? One way is obviously to constantly keep on training new models, right? So using this continual learning approach. But that's usually requires quite a bit of time to continue to learn. So I think what automated machine learning systems also need to be able to do is be able to fall back to more robust models, right? By quickly switching out variables that drift, and again build new models that are not kind of subject to that drift. And really the cutting edge of this right now is put on top of that also the fact that we are changing the world, right, with our predictions. In order to even automate the process of acquiring the data, right, that we need to learn our models, we need to actually keep track of in which cases we intervene with machine learning, where we actually use predictions to do some action, right, in which cases we don't, so we can better explore and better acquire data that we can use for further learning. Good. References here. If you want to learn more about some of these open problems, I highly recommend Rich Karuna's talk from an ICML workshop in 2015. There's a book on automated machine learning, method systems and challenges that I also highly recommend. It's from the leading research group in this area. If you want to get more started with the basics, I recently did a full-day course in a summer school, and you can find the notebooks on my GitHub. Without saying that, I think that's pretty much the end of my talk. Yeah, thanks. I think we have time for questions, if there are any. No questions.
So you mentioned, first of all, thank you very much, very interesting. You mentioned Bayesian optimization and the hyperband. Do you find them really working for neural network cases? I mean, like, I know hyperband was invented for the neural network, but still, did you see them actually in practice work, or are they more for tabular data with some other more classical machine learning methods like forests and things like that?
Yeah, I mean, I'm pretty biased there. I say that right out because my experience is not so much in neural networks, specifically not in architecture search, right? So Bayesian optimization, in my point of view, works pretty well, and I would also expect in neural networks. So if you have a standard multi-layer perceptron and you just want to optimize maybe some of these parameters, that is, probably better suited than obviously just random grid search or some even heuristic versions of that, right? So yeah, I don't have a lot of experience, I would say, specifically in that area. So I would